Okay, so welcome back. So we just had been talking about soft thresholding and these problems of minimizing a square error loss plus an L1 penalty term. So let's go back to the question and let's go back to the context really quickly, just to go back over it. So, I mean, the reason you would use soft thresholding is if you just want to have some smooth nonlinear operator that sends your y's to 0, but it happens to be the thing that minimizes this objective, right? Sends the y's that are small to 0. And we'll see this is commonly used in wavelet methods, and we'll see an example of that in a minute. But at the moment, I just asked you, if we're trying to minimize this objective, which is some function of beta, and we know that the problem is separable. It's equivalent to minimizing individually each of the components of beta, and each of the components of beta are they are arguments to a function, this fi of beta I, which is equal to the following thing. So this is a univariate function, and we're just trying to minimize this. Right? And I claimed that its minimizer happens to be soft thresholding. So soft thresholding, the basic idea is that we have our b is equal to yi minus lambda or yi plus lambda, depending on whether it's positive and greater than lambda or negative and smaller than negative lambda. And it's 0 if yi's absolute value is less than or equal to lambda. Right? So this is the picture we should have for soft thresholding. Okay. So here's the solution, and I mentioned that you should probably go through this definition of the subdifferential. So let's just start by finding what the subdifferential is in this case. So the first thing that we can use is that first property, one of the properties of subdifferentials is that the sum of functions have a subdifferential, which is the sum of the individual subdifferentials. Right? And so if we look back at the function here, we have one function which is differentiable, the square error loss in B. Differentiable, it has continuous derivatives, so we know that all of its subdifferentials are just singletons. It has a gradient, and the subdifferential is just that single element, just contains that single element, which is the gradient. Right, so we can calculate the gradient of this. This part here, we already went over the absolute value. It's subderivative. It's either 1, minus 1. The subdifferential is either singleton 1, singleton minus 1, or the entire interval from minus 1 to 1. Right? And that's when b is 0. Right? So we have that. In the case that b is 0, we'll have an interval for sure. And in the case that b is non-zero, we'll have a singleton. And so we can go through this case by case. So if b exceeds 0, then we have the singleton, and we have the subdifferential of the square error part is just this minus yi times minus beta, or minus b, because this is just the derivative of the square error, this squared term. And then the subdifferential is a singleton lambda when b exceeds 0 for this absolute value, the subdifferential for this absolute value. So we end up getting the singleton, which is this thing, right? Minus parentheses yi minus b plus lambda. Right? And then on the other side, we have if b is negative, then we have minus the yi minus b, the same gradient, the same derivative as before, but now we have minus lambda because the subdifferential of the absolute value is minus 1 in this case. Right? But if b is 0, then we have that it's the entire interval from minus yi minus b, so we still have the same subgradient, but now the subdifferential spans from minus 1 to 1. And so we have minus lambda, and then we have plus lambda here when b is 0. So that's the entire subdifferential. Now, I already said that for convex functions, the global minimizer happens when 0 exists within the subdifferential, and that's by derivative. That's by definition of the subdifferential of this of just what the subdifferential means. That's the first order condition. And so when can 0 be in the subdifferential? Well, when b exceeds 0, then we have that this thing has to be 0 in that case, which would give us that yi exceeds, which would have to happen, it would have to be that yi exceeds lambda, because to set this top part to be equal to 0, we would have to set b equal to yi minus lambda. And so if b is yi minus lambda, when is b exceeding 0? Well, that's when yi exceeds lambda. And so this is the first option. The second option is if this subdifferential, the second line here, is equal to 0. So we just solve for that again. We get that b is equal to yi plus lambda in this case, right? And then if b is negative, that means that yi is less than minus lambda. You just set this less than 0, and you get that yi is less than minus lambda. Right? Now let's consider this following case. We have that we want b to be equal to 0 in this case, for this case to hold, and then we need that 0 lies within this interval, and that's if yi in absolute value is less than or equal to lambda, right? If it's between minus lambda and lambda. And we can see that we just plug in 0 for b here. We have minus yi minus lambda, and we have minus yi plus lambda. For 0 to be in that, yi in absolute value has to be less than or equal to lambda. You can verify that. And so this actually spans all of the cases, right? This is every possible situation, satisfies one of these and only one of these. This is tripartite. So, and then we get a b that satisfies this 0 is within the subdifferential condition for each of these cases. And so we know that this b minimizes it, and this is exactly the soft thresholding function. So, that proves it. Okay, so orthonormal bases. So one of the main reasons why we study soft thresholding is for orthonormal wavelet bases, is in use with orthonormal wavelet bases. So suppose we have a vector, which you can think of as like a time series, y1 to yt. Right? Capital T is the total time length, and we're just observing values of y over time, right? And it's just univariate. Right? And we want to reconstruct y, so the vector is all of y1 to yt. Each yi is a scalar. And we want to reconstruct y, which is a vector, using some w, which is a wavelet basis matrix, times matrix product with beta, where beta is a vector and it has some small sum of absolute values. So that's going to be our condition, is that beta, we're just going to assume that the sum of the absolute values of this beta is relatively small. So we'd like to bias our reconstruction towards this set. Okay. Now w, we're going to assume that it's t by t. So it's orthonormal and it spans the entire space. So this happens with wavelet bases in finite dimensions for orthonormal wavelets, and we are going to assume also that it's orthonormal, which in this case, because it's t by t, that means that w times w transpose is equal to w transpose w, which is equal to I. And so we're going to treat this like a linear model, where y is going to be reconstructed with w beta, where w is taking the place of the design matrix, but it's a sort of special linear model in the sense that it's orthonormal. It's not just orthogonal, but orthonormal, and it's full rank design. So now we want to minimize the following thing. We just look at the ith component squared of this y minus w beta, and then we take the sum of squares of this, but plus lambda times the sum of the absolute values of beta. With the absolute values of beta, the reason why we added this in is because we want a beta that has a small sum of absolute values. Just suppose that you want this. So we're going to talk more about the lasso. This is a specific case of a lasso problem, but it's a special case, so it's sort of natural to work with this first. It's a special case because we have orthonormal design. We don't have just arbitrary design, and it's full rank. So the reason why orthonormal design is nice is that if we look at the square error loss term, we can write it 2 times it as this norm of y minus w beta squared, the 2 norms squared, which is equal to the inner product of y minus w beta with y minus w beta, but we could just throw in this w transpose in here because it's the identity. And then we get w transpose y minus w transpose w beta, and that's just pulling the w into the w transpose into this term. And then this w transpose w, that's just the identity. So that gives you w transpose y minus beta, 2 norms squared. And so we call this, the 2 norm is invariant under orthonormal rotation, sort of rotationally invariant. So we want to minimize this now. This is equivalent to what we had before because I haven't changed this 2 norm objective. I've said that this 2 norm objective here with y minus w beta is equivalent to the 2 norm of y transpose y, w transpose y minus beta. And that's exactly what this is. So it's equivalent to this the original minimization problem is equivalent to this minimization problem. And now it should look like what we saw with soft thresholding. We have w transpose y minus beta without a design matrix. The design matrix is identity. And this is our new program. So this is solved by soft thresholding, but we're going to soft threshold this w transpose y, the ith element of this at lambda. So we just need to apply soft thresholding, but we also need a way to construct this w matrix. Okay. And now our denoised version of y is this y hat, which is equal to w beta. I guess we should write beta hat if beta hat is the minimizer of this. So let's go through an example to make this a bit more concrete. So this data set, it has a bunch of different stock indices over time. So I've just read it in with pandas. And then I'm going to just rename some of these columns so that they look more reasonable. And so this is a Turkish stock exchange data set, but it includes the Nikkei index and some other indices, or some other indices that seem to be pegged to some currencies. Okay, so if we just describe it, we see that there's no missingness. The means are they're similar in some sense. They seem to be commensurate, although some are higher than larger than others. Their standard deviations are all, relatively commensurate. They all seem to be on similar units, and if you think of these as stock returns, then that's reasonable to think of this. We can also look at the info to make sure that the types are all correct, that there wasn't some problem with importing your data. Okay, so I'm gonna in pandas you want to set your index to be this date, so that we know that we're indexing by date and everything else is a variable over time. And then if we just plot one of these, we get something that looks like this, which are the values of this stock over time, the daily values of this stock over time. We could, for example, look at an autocorrelation plot of this, and we don't see any obvious peaks in the autocorrelation. Then we could do this for the other indices. We see some periods of higher volatility and lower volatility, so on. Okay, we'll do this with Nikkei as well. You see some interesting patterns here of sharp increases and then some gradual decreases on average. Okay, so what I'm going to do is try to extract what I'm going to call the volatility. So we have, it's not exactly clear if there's like a big trend in the mean here, but there's definitely trends in the volatility. There's regions of high volatility and regions of low volatility for these indices. So we're going to try to do this by doing a rolling average, which is a 7-day window. So we're going to take the mean within 7 days of each stock, and then we're going to subtract that out, and then we're just going to square the entries. And so what this will do is we're hoping that we've removed the local trends in the mean, and then by squaring it, the hope is that the expectation of that square is going to look something like the local, the variance of that entry. Right? So if we look at this for the Nikkei index, it is has regions of sorry, this is just removing the mean, and so we have that the mean is removed. It seems to be roughly centered around a 0, is to be expected. And then when we look at the squares, we get these very large entries here, very large entries over here, small entries over here. So this actually seems to be reasonable. Now what I want to do is extract regions where there are very high volatility, and I want to actually reconstruct what I think the local volatility is. So this is where the wavelet basis is going to come in. So a wavelet basis in this context, it's going to be a T by T matrix. And the basic idea is that each of the let's see, it would be columns of the wavelet basis would correspond to a vector in this time, which is going to allow us to extract a certain trend here. So let's see what this means. So if we look at the first column of this, the 0th column is constant here, so we'll see that in a minute, I think. But the first column, it's constant until the midpoint, and then it drops down, and then it's constant again, but it's negative. Right? So this is a Haar wavelet basis in particular. That's what the name of this is. And it's a balanced Haar wavelet basis. And the idea is that if I take the inner product of this wavelet basis with one of these signals, so say this signal, then it's going to take the average. In effect, it's going to take the average of this first half of the volatility and the average of the second half of the volatility and do a weighted difference of the two. So it's really picking out what the overall change in volatility at this midpoint is. Right? And so if I were to threshold it using soft thresholding, then if that overall change is really small, then its corresponding coefficient is going to be sent to 0. But if it's significant and large, then that's going to be roughly retained. And if we look at other wavelet bases, the way that this Haar wavelet basis works is that it's going to then subdivide the remaining intervals after we do that initial split. So we split it in half, and then we subdivide it over here. And then this wavelet basis is supported over this first half now. This wavelet basis is supported over this first half. And you have it's split again in half. So this is at the 1/4 line. And then it's positive and large for the first 1/4. It's negative and large for the second 1/4, and then 0 elsewhere. And then if you look at the next wavelet basis, it's going to continue to do this discretization. If we jump over, then we see that there's a wavelet basis corresponding to the other side. So the way that I've ordered these wavelet bases is maybe non-standard, but it doesn't really matter. They're ordering. And then the basic idea is if I take an inner product of this with the signal, then it's going to take the last half, and it's going to take the average of the 3/4 and then the 4/4 and take the difference of those two. So it's picking out what the overall difference between this region and this region are. And that's what that beta, the coefficient that corresponds to that wavelet, is going to give you. Is if this is significantly different than this, then that beta is going to be non-zero. That's the basic idea behind soft thresholding of these hard wavelet bases. So we can verify that it's orthonormal. We take W transpose W, and we could subtract off the identity matrix and sum it, and we can take W transpose, subtract off the identity matrix and sum it, and it gives you roughly 0. Okay, so I'm going to define soft thresholding, and I guess I should mention here, or I should have mentioned a little bit ago, that if you want, you can look at the Jupyter notebook that corresponds to this and see the actual construction of this hard wavelet basis. I just suppressed those slides because it takes too long to go through them. But I actually construct them by hand because it's a little bit tricky how to do this for unbalanced, for vectors that are not of length some power of 2. It's a little bit tricky, but it's not too hard. So if we do the soft thresholding, then the basic idea is that you subtract off lambda if y is positive, you add lambda if y is negative, and minus negative lambda, and then it gets zeroed out if y is in absolute value between negative or less than or equal to lambda. And so this is going to apply soft thresholding in the case that y is in absolute value is less than lambda. Both of these evaluate to 0, so it returns 0. And this actually can be applied to a vector, right, because it's just going to do these operations element-wise in the array case. So if we look at this, we can actually apply this to all of the indices at once. So here's all of the indices. And I made this an exercise just so that you can get back into, get you engaged again. But you can access these values, the values of this data frame, just by doing .values, and that gives you a NumPy array. And these are the 9 stock indices over time. You can apply the wavelet. I want you to apply the wavelet transform constructed above, and soft thresholding with different values of lambda. So I want you to change lambda. Start with lambda being relatively small, perhaps. And what you should see, if lambda is small, then it's going to have a smaller impact. Soft thresholding is going to have a smaller impact on your betas. So when you do soft thresholding, you get a beta. It's modified based on the soft threshold. And then you can reconstruct with W dot beta. And so as lambda increases, you should be it should be augmenting more and more and doing more and more denoising to the y's. So what you should do is you should apply the wavelet transform to y, do soft thresholding to get your betas, and then apply the W again to that reconstructed beta, and do this for different lambdas. Just plot the results in the same way that I plotted this here, so that we can see it kind of lined up with what I'm showing here. This is the original data. Okay, so and just remark on the effect of the changing lambda. So give that a try. And when you're doing this, some lambdas are just going to give you trivial results. Try to find a range of lambdas that are going to give you non-trivial results, so they're doing some thresholding. So you don't have to go crazy with how you do this. Just vary lambda until you start to see some soft thresholding actually happening, some things getting sent to 0, and then try that, and then maybe double or divide that lambda multiply that lambda by 5 or 10, and get a couple of ranges. I'm expecting you to see, at least one where there's very little thresholding going on. There's not that noticeable of a change. One where you see a pretty noticeable change, but it's not dramatic, and then one is a dramatic change to the reconstructed y's and when you're doing denoising. So actually, I'm going to keep going with this video. Let's just pause it here because there's not any content after the solution. So just pause it, try to answer this question, and then start it up again when you think you have a reasonable answer. Okay, so here's my solution, and it's actually pretty easy based on what I've given you, but it might not be obvious. I sort of set it up so that it's pretty easy to do this. So if we do W transpose against the TSC vol dot values, that is a whatever it is, 10 by capital T matrix, or sorry, a capital T by 10 matrix. And W transpose is a T by T, so that actually will work, and it's actually just going to apply the W transpose to all of the columns, which is exactly what we want to do. So you can actually do this simultaneously for all of the stock indices. I'm going to set lambda equal to 0.0001, and then apply soft thresholding. That soft thresholding is done element-wise, and I want to do it element-wise to all of the stock indices and all of the wavelet coefficients. So I can just apply it to this whole matrix, which is this TSC wave, which should be T by whatever, 10 or 11. And I'm going to apply it with lambda. And then we end up getting back betas, which is actually a matrix of betas because we're doing this simultaneously for multiple indices, which you can think of each of those as a vector. And then to reconstruct it, we just do the matrix multiply again, only with W, like I said before. And now let's just, this is kind of a hack, but I'm just going to assign all of the values to that, a data frame of that same size. I wouldn't do this if this data was large, but it's not large, so I'm just doing a quick and dirty thing to get it back into a data frame of the right size so that I can plot it easily. Okay, so this is after soft thresholding with lambda equal 0.001. If we look at this, it doesn't seem to be doing a whole lot. Let's focus on S&P at this very wiggly portion. If anything gets thresholded, it's going to be something like that. So we have some of those seem to be getting thresholded out, the S&P in this extremely wiggly portion, but most of the time, nothing is getting really denoised. If we set lambda equal to 5 times that, so 0.0005, then we get these longer regions of constant values, and that's what our wavelet thresholding is supposed to do, is give you these long constant regions, and then if there are spikes, it'll pick out those spikes. So actually, this, in terms of a denoiser, this seems to be doing pretty well. And this is at lambda equals to 0.0005. So if we multiply that by 2 and get 0.001, do the same thing, then we end up getting that you have these large regions that are completely thresholded out. So if you look at this EM stock, there's only 1, 2, 3 constant regions that are reconstructed. So you know that the betas that are returned, most of them are thresholded out. Most of them are zeroed out. And the only ones that seem to be not zeroed out are the first wavelet, which is the 0th wavelet, which is the father wavelet, and then one of these, at least one of these wavelets, which has a breakpoint at the midpoint in the first part. So if we look at EM, let's go back to the original data and just see if that's likely to happen. Yeah, you have high volatility here in this first 1/4. You have low volatility here, and then you have moderate volatility here. Yeah. And if we look at what it reconstructs here, this is actually kind of interesting. You have that EM is, it's not thresholded right there. So this is the hard wavelet basis is giving us the it's giving us coefficients which correspond to how different adjacent portions of large adjacent portions of this volatility curve are. There's nothing here about no modeling assumptions used here, so there might be, suboptimal properties of using, for example, the square error loss with volatility. It might not be an appropriate loss, but I wanted to mostly demonstrate the use of soft thresholding and give you a practical application of what I described to you, which was soft thresholding. It also gave us an opportunity to use these the subdifferential and think about the subdifferential. But I'd also like to emphasize that the subgradients and subdifferentials, they're supposed to take the place of gradients. When we're talking about convex optimization, they necessarily exist, and they have that meaning in the sense that if 0 is in the subdifferential, then you've found a global minimizer. But in general, we are going to use subgradients even in the non-convex setting, and we'll talk about that a little bit when we get to neural nets with ReLU activations. But in this case setting, it's instructive to think about convex optimization because we use convexity just to define them. But yeah. So thanks.